So you have a wooden block, and it's got a mass of 10.2 kilograms. If you multiply that by 9.8, you get 100 newtons. So it's a 100 newton mass. The block is supported by a smooth horizontal concrete surface, and they give you that the coefficient of kinetic friction between the wood and the concrete is this is, by the way, it's mu, I guess. It's a Greek letter mu, sub k. A 5 Newton horizontal force is applied to the block, pushing it towards the right, and at this instant of time, the block is sliding to the right at a speed of 5 meters per second. What is the force of kinetic friction of the surface on the block, both magnitude and the direction? 84% of you answered 10 newtons to the left, which is also what I liked. But I think what you have to do is let's draw the free body diagram of this block. So when you draw a diagram, you draw the object of interest as being a dot, and then you draw all the forces you can think of that are acting on it. So you've got the weight acting down, and we already said that the weight there is 100 newtons. You've probably got the normal force acting up, I guess. And then you've got somebody's pushing it, F, okay, of the hand, right? Somebody's pushing it that way. And then since it's sliding to the right, I've also got a frictional force backwards, F sub k. And we have an equation, F sub k just equals the normal force times mu sub k, and we have mu sub k is 0.1. So what we don't have is the normal force, but in this case, if we define x to be to the right and y to be positive, then I would say that a sub y is equal to 0. And what that means is F net in the y direction is also equal to 0, because you're balancing those forces. And that's going to be equal to all the positive forces minus the negative forces. So what that means is that N equals W, which equals 100 newtons. So now that we have normal force, we can plug it into there, and we get 100 times 0.1 Fk, and you get Fk equals 10. 10 newtons. And then I've drawn it as being to the left. It's just opposite the velocity. It's this green Toyota Corolla parked on a flat, horizontal pavement. If you're going to draw the free body diagram for this car, which forces should you list on the free body diagram, should you draw? Responses? Yeah, you don't draw static friction because it's not needed in this particular case. I really like that. If it was on a hill or something, or if someone was trying to push the car, then there'd be some static friction. But if you just leave it alone, static friction naturally just goes to 0. It self-adjusts. Again, you got a wooden block. It's the same thing. It's a 100 Newton weight Newton block, so its mass is 10.2 kilograms, conveniently. And it's on a smooth, horizontal, concrete surface. And now you know that the coefficient of static friction is equal to 0.2, which is about twice as big as the coefficient of kinetic friction. Now, 5 Newton horizontal force is applied to the block, pushing it towards the right, but the block does not move. What is the force of static friction of the surface on the block? So a lot of people got C, definitely correct. So the whole 0.2 thing was just to throw you off. Don't get mixed up. There is no equation for static friction. And so I can show you how you do this. It's simple. You just draw a free body diagram. There is normal force acting up. There's the weight acting down, which is 100 newtons. You've got this force pushing it to the right, which is 5 newtons. And you've got the static friction force over here. You've got the acceleration in the y direction equals 0. The acceleration in the x direction equals 0, because it's not moving. So F net in the x direction is equal to 5 minus F sub s. F sub s, and that's equal to 0. So F sub s equals 5 newtons. And it has to oppose that pushing force, so it's to the left. A wooden block of mass 10.2 kilograms has a weight of 100 newtons. The block is sitting stationary on a smooth surface. Coefficient of static friction between the wood and concrete is 0.2. What is the maximum horizontal force you can exert on the block and have the block remain stationary? 20 newtons. There we go. Okay. You guys got it. All you do, there's a normal force. There's going to be some weight. Since the F net in the y direction is equal to 0, this means that the normal force is equal to the weight. And so if you've got this pushing force and static friction force, Fs equals Fs max, mu sub s times the normal force. Here I have Same situation. You've got a applied force on, from somebody's hand, pushing on a crate towards the right. The idea is that it's pushed with 3 different forces in 3 different cases, as shown. And it's the same mass crate. And in all these cases, the acceleration is 0. So the first 2 cases, it's not moving. 100 newtons, 120 newtons. And the second case, she gets it moving, and she's pushing with 130 newtons. But the velocity is constant at 1 meter per second. In which case is the magnitude of the friction force of the floor on the crate the greatest? Ooh. So the one that I like there, I think it's C. Basically, in all these cases, it's the same free body diagram, which looks like this. You've got the normal force acting up. You've got F of the push or something like that, whatever this, it's a normal force, I guess, but it's normal force from her hand. This is the normal force from the floor. This is the normal force from the pusher's hand. So this is, by the way, of the crate. Pick the object. There's going to be the mass of the crate times G pulling down, and there's going to be some frictional force acting backwards. And it actually is F sub S in this case, F sub S in this case, and F sub K in this case. But the acceleration is 0 in all 3 cases. And so I think that in all 3 cases, the frictional force equals the pushing force. So it's this has got F sub S is equal to 100 newtons. This has got F sub S equals 120 newtons. And this has got F sub K is 130 newtons. Empty box is on an incline and it doesn't slip. What happens, so it was a box full of rocks, what if you add more box? It eventually slips, doesn't slip, or it depends on the angle. So what I was looking for is that it doesn't depend on mass. Who voted that it eventually slips? I mean, eventually, I guess, if you added enough rocks, maybe the whole surface would break or something like that. Theta max doesn't depend on mass. So if it was good for one mass, it'll be good for another mass. Remember, there's that equation for terminal velocity. Let's say we have 3 parachuters. They all have similar parachutes, I guess, and they're falling down. They've all reached their terminal velocity. They're all happily falling towards the ground. Which one's falling fastest? However, you're saying C, the more massive guy, is going fastest. Certainly, the density of air is the same in all 3 cases. But maybe if it's the same parachute, we can maybe assume that it has the same drag coefficient and the same area. And so what is different in this equation is just the mass. More massive objects with the same exact shape are going to fall faster. They're going to reach a higher terminal velocity. Which falls faster? Large raindrops or small raindrops? Okay, so the one that I like is large, and I'll show you why. So both the mass and the area go up, but I would say the mass goes up in proportion to the volume, which goes up as r cubed, and the area goes up proportional to the area, which goes as r squared, right? So as things get bigger, the mass to area ratio does increase. So if we assume, for example, a sphere, then I would say that volume is 4/3 pi r cubed, and the area is pi r squared. And density of water is 1,000 kilograms per meter cubed, is constant, and that's equal to the mass divided by the volume. Okay? So I would say that the mass is equal to the density of water times 4/3 pi r cubed. So you can plug this into there, I guess, and you can also plug in the area. So you get V terminal is equal to the square root of 2 times 4 pi over 3 times r cubed times rho water, which is different than rho air, times G, divided by rho air times C. I don't know what C is, it's some number, but it's going to be the same for small and big raindrops if they're both spheres, I guess, times pi times r squared. So then, if you look carefully, this r squared cancels the cube on the top, and you get an r on the top. And a bunch of these other things cancel out, but I got that V terminal is equal to something like 8 times rho of the water times G times r divided by 3 times rho air times C. So there's a bunch of constant things, constants, times r. Bigger drops have fall faster. A wire has a length of 1 meter, but when you suspend a 1 kilogram weight from the wire, and the other end of the wire is attached to the ceiling, when you hang that 1 kilogram mass, it gets a little longer. And now the total length of the wire is 1.01 meters. So if you take off the 1 kilogram mass and hang a 3 kilogram mass, what will be that length of the wire now? 76% of you got 1.03. So that's the basic idea, that delta L has gone up by a factor of 3. L0 is the 1.00 meters, and delta L is equal to 0.01 meters when F is equal to mg and m is equal to 1 kilograms. So a 3 kilogram mass means that's 3 times the force, and so what this means is it's going to be 3 times the delta L. So delta L is going to be 0.01 meters times 3 is 0.03 meters. And so the final L equals L0 plus the delta L.